Hi everyone. Today we're going to start on chapter 11. So in chapter 11, what we're going to start to do is to talk about second order differential equation and probably eventually go talk about even higher order differential equation. But they are very specific type. So let's get started on this. So we'll consider the following differential equation first, which we call linear constant coefficient differential equation. A linear constant coefficient differential equation is in the form of y double prime plus by prime plus cy equal to some function f of x. So notice what's the important feature of this equation is the following, is that the left side of this equation, well, technically speaking, it could be left or the right side, depending on which way you orient your equation, but for this expression, I'm referring to the left side. The left side of this equation involve basically the following. Involves sum or difference, of course, of, here's the important word, constant multiple of y and or its derivatives. So it's literally basically what you have on the left side of a linear combination of y and its derivative. Okay, and this one actually I probably should specify. This one is a second degree differential equation. So maybe I would put that in here. And of course, second order differential equation. Of course, we could do third order, fourth order, and on. And when we do that, we just basically have more higher derivative with more constant coefficient in front. Show you some example of this type of differential equation. And before we talk about like why are these important, so some example would be the following. So the first one, how about this one? Y double prime minus 2y equal to x. So in this scenario right here, basically what we have is b would be 0. Notice there's no y prime. C would be -2. And then f of x would be the function x. Okay. A second one could be this one. Y double prime plus 3y minus plus 2y, 3y prime plus 2y equal to e to the x. So then this one, you have b equal to 3, c equal to 2, and then f of x is equal to e to the x. Now notice that both of these have no coefficient in front of y double prime. And if you do have a coefficient in front of y double prime, what you expect it to do would simply just be divide out the whole thing. So someone might be thinking, can I do ay double prime plus by prime plus cy equal to f of x? Yes, you could. But we actually would prefer the highest power or highest derivative of our differential equation to have a coefficient of 1. So they make the rest of the equation easier to look at. Okay, so that's the reason why it's written this way. However, I did keep the structure of using b and c as the second and the third coefficient instead of changing it. Okay, so both of these are basically typical second order constant coefficient linear differential equation. And they are also, if you want to write it down for yourself, you can. They also refer to as non-homogeneous because f of x is not 0. So something important to pay attention to is if f of x is equal to 0 function, then the differential equation is called homogeneous. Okay, homogeneous. So already we learned quite a few different adjectives to describe it. We have in order, this describe the highest derivative involved. We use the word linear a lot because these are the type of function that we want to deal with. We use homogeneous versus non-homogeneous a lot because that's a big difference between how we deal with those two type of equations. And then now the new term is constant coefficients. Okay, and you understand why constant coefficient is important, and that form one of the most simplest type of differential equation that we can solve. Now, why is this type of equation, a second order differential equation, important? Well, because the following. Second order differential equations are extremely important to study because the unknown function can represent position, and therefore making its first and second derivative to be velocity and acceleration. So therefore, it's particularly important in physics when we try to learn about motions. Velocity and acceleration. And as we learn that a lot of the forces involved will be dependent on velocity acceleration, and especially when you talk about things that compress, then the position will determine the force involved, and if the object is moving, then it could have momentum, and it also could have resistance, and resistance is based on velocity, and then we all know that force is actually based on acceleration. So therefore, a second order differential equation actually will allow us to relate all the forces involved together into one equation, and then try to use the solution to a differential equation to kind of model the movement of an object if we know all the forces are involved. And we actually will go do some application of this later on in a different section, or maybe a little bit of it in this section also. Okay. Now, and even if you don't want to talk about it from a physics standpoint, at the very least, first and second derivative can be used to at least do the following. Can be used to identify the slope and the concavity. So that's the most basic interpretation of what these two derivatives would do of a graph of a function. So therefore, it's important to study these two derivatives, and as well as any differential equation that's come from these two derivatives, because of that, the fact that they have a lot of application where it's purely mathematical about slope and concavity of a graph, to maybe more useful in application in physics, where we go talk about acceleration and velocity. So now that we're ready to talk about higher order differential equation, what I want to do is introduce to you a kind of new way to rewrite a differential equation. And once again, the idea here is to try to rewrite it into a different notation that help us understand what's going on better. So the notation is actually something that we have talked about back in chapter 3, differential operators. What's so special about differential operator is that differential operator act like finding the derivative, act as an operator, which allow us to apply to a function in this case. And most important of all is the following, is that differential operators are linear operator. And we can actually combine different linear operators together to form some very unique and very complicated differential operator, and then allow us to actually use the fact that they're linear to help us understand what's going on. So show you the basic concept. Okay, we will do the following. We will let d be kind of the derivative, or maybe technically the differentiation. So that's the process of finding the derivative of a function with respect to an independent variable. We're not going to specify this independent variable from the operator notation, but it should be clear what it is from within the problem. So for us, most likely, this independent variable will be x if we are talking about basic xy or single variable function, or it could be t. So we'll usually use x if we have a real value function. And we most likely call the real value function y. We usually use t when we have a vector value function. And most likely in this case, we probably talk about x, y. Okay, then we'll use t as the independent variable. Because remember from what we learned last year, when we have a vector value function, we probably interpret our function as parametric. So we use t as the parameter. But if it's real value, then we expect it to be an explicit function. Then we use basically x and y to be the input and the output. And so what does this function, what does this differential operator do? Basically this, so that d is defined to be the following. Okay. Okay, maybe I'll start on your lines that can't run a room. Okay. So how do we define d? Well, d is defined as the following. If I put a function inside, it will give us a derivative of that function. With u being a function, of the independent variable. So such as u of x, or likely to be u of t. So basically what does d do is that d simply just form the derivative, or basically indicate that, oh, you're looking for the derivative. So we can now define some example of differential operator. Okay? But before we do some differential operator, do recall from the following. We call differential operator, d, is linear. Oops. So what does that mean when I say it's linear? It implies that if I take d of, let's say, two different functions, u plus v, that become d of u plus d of v, which basically meaning u prime plus v prime. Pretty simple. And if I do d of some constant multiplied by u, then that just becomes that constant times the derivative of u, therefore just becomes cu prime. So those are the two basic concepts of why differential operator d is linear, because it satisfies both of these properties. All right. Because of the fact that it is linear, since d is kind of close, provided that we keep them within a specific subset of continuous function, so that I can actually make it close. Since d has closure under certain subset subspace, we can define d square of u to be d of u, which basically become u double prime. Okay. And this definition extends to higher order. So if I do d to the third, that means basically d of u. Let's see, good. That would be d to the third triple prime. And then this continue on to d to the nth u. That just becomes u to the nth power. Is any of these new to you? No, it's not. You have seen this. You know what they are already. Okay. Now, with that being said, now we can define some example of differential operator. These are custom differential operator, meaning that they're not just D, but they have other things to it. Or maybe I should say example of linear operators using D. So, and it's pretty simple. So I can define a differential operator D plus 2 of y. And basically what does that mean is this. That basically means is d of y plus 2 times y. And therefore just become y prime plus 2y. So y prime plus 2y is can be written as d plus 2 of y. All right. And similarly, I can also do this. I can simply do d squared minus 1 of y. And that just becomes d squared of y minus 1 of times y. Then that just becomes y double prime minus y. Okay. The interesting thing about differential operator, writing using differential operator, is that it allows us to actually combine linear operators together as well as break them apart. So give you an example. So one interesting thing about it is that we can actually kind of quote unquote multiply or factor linear operator like this. Example. Imagine I ask you to do d minus 1 of d plus 1 of y. Okay, what would that entail? So let's find out. So therefore, I basically operate in order. So I'm going to say that is d minus 1 of d plus 1 of y. Remember, linear operator get multiplied when you plug in one after another. So even though the notation kind of read out as multiplying next to each other, but essentially what you're basically doing is kind of apply one after another. So that would basically tell me that's d minus 1 of y prime plus y. And now based on the linearity of the operator, I can say that's just d of y prime plus y minus 1 times y prime plus y. So that becomes y double prime plus y prime minus y prime minus 1. And notice these two things cancel out, leave you y double prime minus 1. Notice we already know that's the same thing as d squared minus 1 of y. And notice that d squared minus 1 is actually the same, based on our math, d minus 1 times d plus 1. So therefore, notice that d minus 1, d plus 1, this linear operator is the same as d squared minus 1. Pretty cool, because that kind of worked out to be our difference of two squares. Okay, now give you another one to try out. Oops. So what does that come out to be? So essentially all you do is basically just kind of multiply these two things together, just like what you normally would do with polynomial, except that here you kind of using d like the variable. Okay, so when you do that, this actually just become d squared plus 3d plus 2 of y. And they both actually give out the same thing, and this would come out to be y double prime plus 3y prime plus 2y. And as I say, this allows us to actually factor our expression also, meaning I could say this. If I have this whole process can be reversed, meaning if I have this, I can say that's the same thing as d squared minus d minus 12 of y, and therefore I can rewrite that into d minus 4 d plus 3 of y. Common mistake student made is the following, is that you want to make sure you don't forget the 12y, okay, because it's in the differential operator form, it doesn't have something next to it. So therefore usually students often get confused and forget. All right. So now come the next question, which is, what if we have an equation in this form? What can we do to take advantage of the fact that the differential operator can be factored? So, but before I show you that, I do want to show you how to solve a second order constant coefficient differential equation using method that we already know. Because I want to show you what the solution look like and then tie it to how we actually can form the solution. Remember, the general idea of a lot of the method that we're going to try to do to solve a differential equation is to actually avoid using integration to do it. So I want to show you how to do it with integration, for those that we can actually, and then try to figure out how to take advantage of it and try to come up with a solution. Remember, the general concept is that you have to be able to identify the differential equation by its types, and then based on its type, figure out how to form the solution or figure out what the solution should look like, and then try to just plug in. So the last thing I want to show you is how do we solve an equation like this? Let's say I have this one right here. So how do I solve this equation? So first of all, remember this is a second order linear constant coefficients. Oops. Homogeneous differential equation. Okay, so I think that's pretty much describe what this equation is. So notice that there's they're quite a few different set of words. Okay, 4 different adjectives to describe this one equation. So how do I solve this equation? So the way I'm going to do it is to do the following. So, and this is just to illustrate how to solve a differential equation using differential operator and also try to come up with a method. And eventually we're going to refine this method based on the fact that how the solution come about. So, show how this is done. So first I'm going to do is I'm going to go and rewrite this into a differential operator form. Okay. And then what I'm going to do is this. I'm going to factor my differential operator. And notice that's very easily factorable. I'm going to go and factor into d plus 3, d plus 2 of y equal to 0. Okay. And now to solve the problem, what I'm going to try to do is the following. See, the only method that we know how to do solve a differential equation right now, I mean, other than what you've learned previous year, direct integration, which doesn't work here. Separable differential equation, which doesn't work here. The only one that we can do is exponential multiply or integrating factor method. But that only allows us to solve a first order differential equation. This is a second order differential equation. However, the beauty of the fact that we factor our differential operator is the following. Is that I can now try to separate this second order differential equation into literally two first order differential equations. This is how. We're going to go ahead and let the function y, or a function u, to be equal to d plus 2 of y. And remember, we're still trying to solve for y. But we're going to try to create this intermediate step. And therefore, imply that d plus 3 of u would equal to 0. Now, that is a first order differential equation. And it is still linear. Okay, the fact that we separate and make the substitution still maintain it to be linear. So therefore, now what I can do is the following. Now what I can do is rewrite this into u prime plus 3u equal to 0. And that is a first order differential equation that I can actually solve. I can solve this because the homogeneous, I can actually solve it using separation of variable or exponential multiplier method, which I'm going to do. So I'm going to say m would equal to e to the integral of 3d x, okay, or t if you want to. That we become e to the 3x, be my exponential multiplier. So therefore become e to the 3x u prime plus 3 e to the 3x u equal to 0. And therefore tell me that e to the 3x u prime equal to some constant 0. Therefore imply e to the 3x times u must equal to some constant c1, because I'm going to have to integrate twice to solve this equation because it's second order. So I'm going to call this one c1 for now. And therefore tell me that u must equal to c1 e to the negative 3x. So that gives us the answer for u. So now what I have to do is now try to solve my second equation. My second equation is this one right here, where I now know that d plus 2 of unknown function y would equal to u, which is c1 e to negative 3t. Notice this is also a first order linear differential equation, but this one is not homogeneous. So this one cannot be solved using separation of variable, unlike the previous part. So, but this one I can still do. I can say that's y prime plus 2y equal to c1 e to negative 3x. Now remember, here's usually where mistake come from. Is forgot the y, or just like here, forgot the u. Okay. And so now I'm ready to go through this problem. Again, this is basic exponential multiplier method problem. So I'm going to say m equal to e to the integral of 2 dx. So therefore e to 2x will be our exponential multiplier. So e to 2x y prime plus 2 e to 2x y equal to c1. If I multiply e to negative 3x with e to 2x, become e to the negative x. Now remember, this part come out to be e to 2x y prime equal to c1 e to negative x. So when I take the integral of this, e to 2xy equal to, technically speaking, negative c1 e to negative x. But since c1 is a constant that we don't know, I'm just going to leave it as c1. But don't forget, plus c2, because that's a second integrational constant. And now if I divide everything by e to 2x, then what I have will be c1 e to negative 3x plus c2 e to negative 2x. Several things that are important about look at this solution, that's probably the last one we're going to talk about, is the following. Notice that because this equation is a second order differential equation, that usually indicates that if we do solve it by using integration, I do have to integrate twice. And therefore, indicate that we have to have two arbitrary constants, C1 and C2. As a matter of fact, A very simple concept is that when you have the order of your differential equation would dictate how many constant you have. And therefore, also important to understand is that this function y actually form a linear combination of the following two things, e to the negative 3x and e to the negative 2x. And since e to the negative 3x and e to the negative 2x are linearly independent, this actually form a subspace of dimension 2 because of the fact that it has two arbitrary constants. And therefore indicate that if you do, let's say, a third degree differential equation, then your solution would most likely be a subspace in dimension 3. And then if you're fourth degree, it will be dimension 4 and on and on. All right, I think I'm going to have to stop right here for today. So we're going to continue some more tomorrow on the next video. Okay? Bye-bye.